Welcome back to Jumpstart Honors Pre-Calculus. In this session, we will build on the concept of functions that you learned in the previous session. Today, we'll explore how to read graphs for key features and how to transform any parent function using shifts and reflections. Here's what you'll learn today. In section 1.3, we'll cover the vertical line test, intervals where functions are increasing, decreasing, or constant, and relative minima and maxima. We'll also discuss even and odd functions, as well as the 6 parent functions. In section 1.4, we will dive into transformations, including vertical and horizontal shifts, reflections across axes, vertical stretches and shrinks, and how to combine these transformations in the correct order. Let's start with the vertical line test. A graph in the xy plane represents a function if and only if every vertical line intersects the graph at most once. For example, the graph of y equals x squared passes the test because every vertical line hits the parabola only once. However, the equation x squared plus y squared equals 1, which represents a circle, fails the test because vertical lines can intersect it twice. In this animation, you'll see a vertical line being swept across different graphs. When it sweeps across the circle, it fails the vertical line test because there are 2 intersection points. Then, as it sweeps across the parabola, it passes the test with only 1 intersection point at a time. Next, let's discuss increasing, decreasing, and constant intervals. A function is increasing on an interval if, for any 2 points within that interval, the output value at the first point is less than the output value at the second point. Conversely, it is decreasing if the output at the first point is greater than at the second. If the output values are equal, the function is constant. Remember, we describe behavior using open intervals of x, not y values. Now let's define relative minima and maxima. A value f of c is a relative minimum if it is less than or equal to all nearby output values. Conversely, it is a relative maximum if it is greater than or equal to all nearby output values. It's important to note that while we refer to these extrema as output values, we say they occur at specific x values. In this example, suppose we have a function f that rises on the interval from -infinity to -1, falls on the interval from -1 to 2, and rises again from 2 to +infinity. Given that f of -1 equals 4 and f of 2 equals -3, we can identify the intervals of increase and decrease, as well as the relative extrema. The function is increasing on the intervals from -infinity to -1 and from 2 to +infinity, while it is decreasing from -1 to 2. The relative maximum is 4 at x equals -1, and the relative minimum is -3 at x equals 2. As you watch this animation, you'll see a dot tracing the curve of a function. When the dot climbs, the function is increasing, and this is represented in green. When the dot falls, the function is decreasing, represented in red. The turning points, where the direction changes, are marked as the relative maximum and minimum. Let's explore even and odd functions. An even function satisfies the condition that f of -x equals f of x for all x in the domain, meaning it is symmetric about the y-axis. Examples include x squared, the absolute value of x, and the cosine of x. An odd function satisfies the condition that f of -x equals -f of x, indicating symmetry about the origin. Examples of odd functions are x cubed, x, and the sine of x. Most functions, however, do not fall into either category. In this example, we will determine whether each function is even, odd, or neither. For the function f of x equals x to the 4th minus 2x squared plus 1, when we replace x with -x, we find it remains unchanged, indicating it is even. For g of x equals x cubed minus x, replacing x with -x gives us the negative of the original function, so it is odd. Lastly, for h of x equals x squared plus 3x, neither condition holds, so it is classified as neither even nor odd. In this slide, we visualize the symmetry of even and odd functions. An even function, like x squared, reflects across the y-axis, while an odd function, like x cubed, rotates 180 degrees around the origin. A function like x squared plus x, which does not meet either condition, shows that both tests fail visually. Now let's look at the parent functions gallery. The The key parent functions you should know include the constant function, the identity function, the absolute value function, the square root function, the quadratic function, and the cubic function. Memorizing their key features, such as domain, range, symmetry, and intercepts, is essential as all transformations in the next section will start from these parent shapes. In this animation, you will see the 6 parent functions you need to know. As each function appears, take note of their domain, range, and symmetry. Now let's try some practice problems on graphing functions. First, determine if the function f of x equals x to the 5th plus x is even, odd, or neither. Second, consider a function that has a relative maximum of 7 at x equals -2 and a relative minimum of -1 at x equals 3. On what intervals could this function be increasing or decreasing? Remember to think about the behavior around the extrema. Let's transition to section 1.4, where we'll explore transformations of graphs. Now that we know the parent functions, we will learn how to move, flip, and stretch them to create new functions. First, let's discuss vertical shifts. If c is greater than 0, then the equation y equals f of x plus c shifts the graph up by c units, while y equals f of x minus c shifts it down by c units. For example, if g of x equals x squared plus 3, this represents the parabola f of x equals x squared shifted up 3 units, moving the vertex from the origin to the point 0, 3. Now let's look at horizontal shifts. If c is greater than 0, then y equals f of x minus c shifts the graph to the right by c units, while y equals f of x plus c shifts it to the left by c units. This can be counterintuitive, as horizontal shifts go in the opposite direction of the sign inside the parentheses. For example, f of x minus 3 shifts the graph to the right, not left. In this animation, you will see how horizontal shifts work. Watch as the absolute value function shifts to the right when we subtract 3 from x, and shifts to the left when we add 2 to x. Remember, the sign inside the function indicates the opposite direction of the shift. Let's look at an example of combining shifts. For g of x equals the absolute value of x plus 2 minus 4, we start with the parent function f of x equals the absolute value of x. The term absolute value of x plus 2 indicates a shift left by 2 units, and then subtracting 4 shifts the graph down by 4 units. The vertex moves from the origin to the point -2, -4. Next, let's discuss reflections. To reflect a graph over the x-axis, we use the equation y equals -f of x, which negates the output values, flipping them. To reflect over the y-axis, we use y equals f of -x, which negates the input values, mirroring the graph left to right. For example, if f of x equals the square root of x, then negative square root of x reflects over the x-axis, while square root of -x reflects over the y-axis. In this animation, you'll see reflections in action. First, watch as the graph of the square root function flips downward to become negative square root of x, which is a reflection over the x-axis. Then, observe how it flips left to right to become square root of -x, which is a reflection over the y-axis. Now let's explore vertical stretches and shrinks. For a constant c greater than 0, the graph of y equals c times f of x is obtained from y equals f of x by stretching or shrinking vertically. If c is greater than 1, it results in a vertical stretch by a factor of c, pulling the graph away from the x-axis. If c is between 0 and 1, it results in a vertical shrink by that factor, pushing the graph toward the x-axis. For example, y equals 3 times x squared stretches the parabola, making it narrower. In this animation, you'll see various transformations applied to parent functions. Watch as shifts, reflections, and stretches are demonstrated. I encourage you to predict what the next transformation will be before it happens. Now, let's discuss the order of transformations. When multiple transformations are combined, it's important to apply them in the following order. Horizontal shifts first, then stretches and shrinks along with reflections, and finally, vertical shifts. Think of it as working from the inside out, handling what happens to x first and then what happens to y. This consistent ordering helps prevent errors. In this example, we will describe multiple transformations starting from f of x equals x squared to arrive at the equation g of x equals -2 times the quantity x minus 3 squared plus 5. First, we shift right by 3 units. Then we apply a vertical stretch by a factor of 2, followed by a reflection over the x-axis, and finally, we shift up by 5 units. The vertex moves from the origin to the point 3, 5. Now it's time for some practice with transformations. First, write the equation for the function f of x equals the square root of x after shifting left by 4 units, reflecting over the x-axis, and then shifting up by 1 unit. Second, given g of x equals 3 times the absolute value of x plus 1 minus 6, identify the parent function, all transformations, and the new vertex. To summarize today's session, we covered the vertical line test, intervals of increase, decrease, and constant behavior, as well as relative minima and maxima. We learned about even and odd functions, and we explored the 6 parent functions. In the second section, we discussed transformations, including vertical and horizontal shifts, reflections, and vertical stretches and shrinks. Remember to practice these concepts, as they are foundational for our next session on combining functions, composition, and inverses.